What a great crowd for a Tuesday evening at 5:30. This must say something good about MIT. Thank you for being here. My name is Robert Stoner. I'm the Deputy Director of the MIT Energy Initiative, MITEI, for Science and Technology. I'm also the Director of the Tata Center for Technology and Design. We're here today to talk about energy innovation for a net zero future, which is a title that pretty much precisely describes MITEI's mission at MIT and our sole reason to exist. We're here to help decarbonize the global economy. We're not going to do it all ourselves. MITEI emerged from a listening tour that President Emerita Susan Hockfield undertook when she arrived at MIT to begin being the president, very much as our current president did over the last several months. And she heard a rather similar message. What she really heard was, we need to do more as an institution to be engaged with decarbonizing the global economy and fending off this very serious threat of climate change. At that point, not that many people were involved in energy research. Since then, we've helped faculty from across MIT in all 5 schools to become engaged in energy research. And roughly 40% have worked with us over our 17 years in the biz. And over that same period of time, we've deployed roughly $1 billion in energy research in every conceivable topic you can think of at every stage, beginning from seed stage research, just high-risk, interesting, novel ideas, all the way to pre-commercial research, translational research, if you like. Lately, we've begun to shift our emphasis toward deployment, more toward the pre-commercial end of the readiness spectrum. We're keeping the pipeline full at the early stage. We want new ideas to continue to come in, but we're paying a lot of attention to technologies that have been developed to a point at which they appear to have commercial potential, and where faculty and students are engaged with the idea of bringing them there. But they need another year or two of research here to establish that they can meet the requirements that the market will have of them before they go into the commercial arena. We're trying to de-risk them and make them more investable. Our member companies, and we're supported by a large number of companies, are very excited about this, and I think you'll begin to see the impact of this shift in the next several years as more startups emerge from MIT and begin raising money and becoming very visible. But scores already have. And so this is an amping up of activity that in some ways we've already worked. Also, about 1.5 years ago, we launched a new center within MITEI called the Future Energy Systems Center. The Future Energy Systems Center, again, is deployment-oriented. It's recognizing that we're going to begin putting all of this new technology into the energy system, displacing the technologies that are already there and causing a lot of disruption. The investments that are being made are very risky in the early going, because it's not clear how technologies will compete with one another and where they'll settle out and what their role will be within the overall energy system. Will they be economic? Will investors get a return on their investment? What we've been doing is developing a range of analytical techniques and models that we use to answer a wide range of questions that investors and companies who are engaged in the transition have. And it's going really well. In just 1.5 years, we have over 40 members, and they are busily posing questions to us, and it's beginning to enter their planning and thinking. We're not alone in feeling a sense of urgency. The Biden administration has been very active, as many of you will know, and over the last 1.5 years have passed 3 crucially important coordinated laws: the CHIPS and Science Act, the Inflation Reduction Act, and the Bipartisan Infrastructure Law. These work together to inject a large amount of money, which will, over the next 10 years, amount to several trillion, delivered through our tax system, which is the way we subsidize things in this country, to firms that are deploying low-carbon technologies. I'd remind you that the Biden administration has set a goal of reducing by 50% our overall greenhouse gas emissions relative to a 2005 baseline by 2035, and to achieving full net zero energy by 2050. It's incredibly ambitious, and the acts that they've passed are appropriately ambitious. Last year, the administration also released its whole of government vision and strategy for bringing the government, various government labs together in a coordinated action, and published an article, it's a short one that you can find on the web, entitled U.S. Innovation to Meet 2050 Climate Goals, Assessing Initial R&D Opportunities. And in it, they set the stage for achieving our net zero goal. That really is the focus of this evening's presentation. So my job is not to tell you all about that, but to hand off to our panel and to introduce them. So what we're hoping to do, what we're intending to do, is present a panel discussion in which a number of our faculty who are involved in different parts of this vision have expertise and thoughts. And so they share them with you, and then we'd like to have a discussion among the panel and with you about how we can, as a community, do better to coordinate and synergize our activities and perhaps reach beyond where we are reaching now in bringing new technologies forward. So let me introduce the panelists. First on my left is Christoph Reinhart, who is a professor and director of building technologies in the Department of Architecture. On his left is Bill Green, who's the Hottel Professor of Chemical Engineering. On Bill's left is Anuradha Annaswamy, who's a senior research scientist and the director of the Adaptive Control Laboratory in the Mechanical Engineering Department. On her left is Bilge Yildiz, who's the Breene M. Kerr Professor in the Departments of Nuclear Science and Engineering and Material Science and Engineering. And almost last is Dennis Whyte, the Hitachi America Professor in the Department of Nuclear Science and Engineering and the Director of the Plasma Science and Fusion Center, the PSFC. Thank you all for joining us today. And on his left is our moderator, Ann Whyte, who's an Associate Provost and Associate Vice President for Research Administration, as well as a Distinguished Professor in the Department of Nuclear Science and Engineering. So welcome to all of you, and Ann, I'm going to hand over to you now and sit down and shut up and look forward to the discussion.
Well, thank you so much for introducing MIGHTY, introducing the broad research and deep research that's happening here at the Institute. I've been asked to add a few very brief additional remarks to just help set the stage for these panelists, because we want to hear from each of them as individuals, and then, of course, hear about how their collective efforts combine. Because it's only through these collective efforts that we can possibly achieve such ambitious goals that you heard about there from Rob. This Biden-Harris administration announcement of the priorities that will help us get to these goals of reduction of 50% for the greenhouse gases by 2030, 2035, and net zero emissions by no later than 2050, this has to be accomplished by filling some gaps and going after some opportunities. So there were priorities, net zero game changers that were called out, and these were gaps that were floated at the very highest levels of government reports and discussions. And those are why these were picked for this panel. That's one reason why. They were efficient building, heating, and cooling, net zero aviation, net zero power grid and electrification, industrial products and fuels for a net zero circular economy, and fusion energy at scale. I should also mention that these topics were picked for this panel also because they are places where MIT has significant expertise and progress already ongoing toward addressing those gaps. So we're really hoping that with this panel this evening, we can share the information with all of you, with each other, and really open the door for new involvement, for building of new bridges, and kickstarting new collaborations that might really be possible. And that's why it's just such a wonderful thing to do at a place like MIT. So let me turn it over now to Christoph. Please take it away.
Thanks a lot, Anne. Welcome, everybody. Thanks a lot for joining us. Just to understand who I'm actually talking to, is there any MIT student who has a final this week?
He's clear.
Thank you. Shout out for those who have. That's really great. I was really afraid I would be standing and talking to an empty audience because all the students in our program are actually working, and wondered why. Oh, the secret is already given away. Here we go. Why we would have the panel tonight. So welcome. As Anne said, I'm going to talk about building and heating and cooling and how to reduce that. And to get us started here, I'm actually going to show in graphic format, since I'm from the School of Architecture, what you already heard, that effectively the official goal of the United States is to keep global temperature rise under 1.5 degrees Celsius. And what this means is that we have 580 gigatons of carbon left to burn, and we have until 2050 to reach a net zero economy. And how does this relate to buildings? We know buildings right now are responsible for about 40% of carbon emission, so that black wedge is ours, so to speak. And it means in two simple numbers, we have 300 gigatons and 30 years left to have the whole global building stock carbon neutral. So that's our budget and the timeline that we have. So what are we going to do with that? Well, first we have to look at how many buildings we're actually talking about. And what you see here is actually that globally the building stock is going to double in the next 30 years. So we basically have to focus on both the existing buildings, which are 2/3 of what we are expected to have by 2050, as well as new construction. And so if I start us off with a business as usual case, right now business as usual means that we are retrofitting about 1% of the global building stock every year. And we might, by 2050, have solutions for carbon neutrality for all buildings. Then we're going to blow through the whole budget that we have as a humanity, and by 2050, we haven't gotten anywhere. So what we really have to do is we have to focus both on the operational energy of buildings, so how much buildings use while they're being operated, heating, cooling, and electricity, and so forth, as well as the embodied energy. So all new buildings that are being built, we have to start ramping that down, use materials that are net zero carbon. And when we look at this, it's an enormous task. Two simple kind of tasks for us to remember is we have to increase the annual retrofitting rate to 5% per year by 2030. And we have to make all new construction types carbon neutral by 2030 as well. So now let's jump into some buildings. How is this actually possible? What you see here is for 2015, the data for all residential buildings in the US, like the typical per household, normalized per household, what did we use as fuel sources and how did we spend that in buildings? And you see natural gas, propane, electricity is the type of fuel sources that we had. And then we spend 70% on that on heating and cooling residential buildings. So this is where this strong focus comes from. We have to reduce that number. So how are we actually going to do that? I think it's Mark Twain who said, talk is cheap unless Congress is talking. So we just heard about there is a huge amount of funds available in the next couple of years. And so I'm going to tell you a little bit of a story of what an owner of a building might want to do and how that then relates to the grid as a whole. So if you are the owner of a typical home in New England, this is what these numbers are specifically for, and the building hasn't been renovated, old building, you love it, you don't love your utility bills, which are about $1,000 per year, you spend $1,700 on gasoline, and you and your family, if you assume a family of 4, you are spending 16 tons of carbon per year. So, and how do you look as a customer? Well, you are a great customer for natural gas. You're using an enormous amount during the as you see on the right-hand side during the winter months, and your electricity use is pretty constant throughout the year. You have a little bit of peaks due to the air conditioning system that you're using for electricity. So now you're opening the newspaper and people just tell you, oh, you should really get a solar system, do something good for the world and get a heat pump. And you think, yes, I want to do good in the world, so I'm going to place these big heat pumps in front of my house that everybody sees them, and I'm going to fill my rooftop with PV. So what would that do effectively? So you're spending about $53,000 on that, and you get your money back in 10 years. And on paper, you basically end up, since you oversized your PV system, that you get a couple of $100 every year back. You still spend all the money on your gasoline. How do you look on the right-hand side? Basically in gray, you see your old profile for electricity. In yellow, you see the monstrosity of a client that you are. You're basically somebody that dumps huge amounts of electricity when nobody wants it in the summer into the grid. And you still, you increase the peak by 70% due to your heat pump that you're having. So the utility doesn't love you particularly and tries to convince you to something else. And so then hopefully you get a good contractor who's working with you and say, well, you should get efficient appliances, LED lighting, smart controls, Mass Safe and other institutions pay for you to insulate your wall. And rather than having this oversized PV system, make the PV system as large as you actually need it. And when you do that, you basically now are dealing with 10 years of payback time for a system like this. And when you look on the right-hand side, what happened, you still moved your electricity peak to the winter, but at least it's the same height as it was before. So that just shows you it's of paramount importance that we retrofit our buildings. But then you don't like it that your roof is not full of PV. Is there any more money to be made? So you're going back and you're starting filling the free area up again, and you're buying an electric car, nice Tesla, your neighbors are green with envy. So what happens then? You actually end up in a situation where you have no money that you spend on driving your car around anymore per year for operation. Your bill is, and your carbon emissions are zero. And since gasoline is quite expensive, well, not really, but relatively speaking, in 8.5 years you basically get your money back for the steal of $48,000. So this just shows you that it's a really complicated system and very different things that you can do. And you can actually improve the peaks even more if we start integrating the controls better between how your Tesla is charged and discharged and the grid overall. So now your member might wonder, is anybody willing to spend $50,000 on retrofitting their building? We recently, through the center that Rob mentioned, did a survey with 1,500 homeowners with National Grid territory, and this is basically the deal, no deal line in terms of willingness to pay that we found. So 90% of owners will spend certainly $500, but you still have a respectable 30% of building owners surveyed willing to pay $50,000. So that's a seasonal portion. Unfortunately, or not surprisingly, if you overlay income level, is that the higher income levels are going to do this, that have money for this. So what this means is if we really want to have this type of development on a wider scale, we have to be very clever on how we're going to spend all this money that Rob promised us earlier today and make sure that everybody is basically benefiting from this. Right? So just quick words on new construction. This is a trend, passive house that you probably heard of that is really taking on in New England. I've taken this slide from Jeff Geisinger, who is the sustainable director of an architecture firm here, mid-sized in-town util. And just to show you, they are working on 8 of these multi-unit residential passive houses. So these are extremely low energy residential buildings, really good envelope, tight envelope, and good ventilation systems. And a fair number of these projects include affordable housing as well. So this is really just a sweet spot here right now that is worthwhile paying attention to. The reason being that once you have multi-unit residential buildings, you share a lot of internal walls, and the envelope is the expensive part. So there are just some super interesting economies of scale that are happening here, and you'll see a lot more of this going forward. And maybe just looking finally at commercial buildings, there it becomes a lot harder to get net zero. So if you look at a building like here from Snohætta in Norway, this is a net zero 7-story office building. That's really difficult to do. You basically have to start looking into the building. So far there were no compromises on how people live in the building. You have to look at appliances. You really have to go all out. The one in the middle, that's even harder. That's the new School of Architecture and Design in Singapore and NUS. That's a net zero building, 5 stories high, in an incredibly humid climate. That's very, very difficult to basically find their passive systems that still manage to be as efficient to use only the rooftop for PV. And then finally, that is an Austrian example, kind of combination of passive house standard and supermarkets and so forth. And just linking to our discussions later on, this is my, in case you're nervous, last slide. I'm basically just want to talk about, is what we're doing right now a good idea? So what you see on the slide here, this is currently the Tesla driver solution where we effectively use photovoltaic that peaks in the summer while we are needing a lot of electricity for our home, for our heat pumps in the winter. So from a physics and seasonality standpoint, that's what we're doing. That's what we want to do more and more. That's not really a great idea. So what would actually be better is what you see a lot more in Europe, is that you also put in biomasses and other sources. You have district systems, so you combine multiple buildings, you heat and create electricity at the same time. Why is that good? Because you are now creating a lot of electricity in the winter, because this is when you burn a lot of biomass. And of course, when you put these two systems more together, then you have 2 straight lines over the year, which is good. So rather than just putting maybe all our eggs in that heat pump basket without having any idea where the electricity in the winter is going to come from, I think looking at other sources of heat will be incredibly useful. And with that, I hand it over to Bill.
Thank you. See if I can find the... Do you know, does it just keep going? Yeah. Where is the mouse? Oh, there it is. You see it?
We lost the pointer.
Yeah.
So funny.
Can you help us?
Oh, there was some movement in the corner.
Okay.
Yeah.
Yeah. All right.
Okay, so I need to close this. And, where is mine? Hello. It's all in one. Good. All right, thank you very much. Can you turn it so you can see? Go one further. Okay, good. All right. All right, so I'm going to talk to you about aviation. As you know, we like to fly around, and as the world gets richer, more and more people like to travel. But of course, this has a problem. That all that wonderful travel that we can have is associated with a lot of emissions. And the emissions affect the climate, and they affect air quality, and so human health, in a lot of different ways. And so if you try to add up the harms from the different emissions, it turns out you have a lot of climate harm, primarily from the CO2 emissions, some also from the formation of contrails, which tend to net warm the world a little bit. And also you get a lot of air quality problems, some from particulates, but mostly from the NOx that's emitted by the jet engines as they fly. And the total harm is about $860 per ton of jet fuel that's burned, which coincidentally is similar to the total cost. The economic cost of jet fuel is about $840 per ton. So the cost that the airlines are paying for the jet fuel, or the passengers are paying for the jet fuel, is only about half of the true cost to society. And the other half is borne by all of us by the fact that it's affecting the climate and it's causing medical problems for people. So how can we fix this? There's kind of three directions. So one is you can change the way you operate aviation to try to minimize the contrail formation. I'm not going to talk about that. You can also reduce the CO2 emissions by going to low carbon fuels. I'll talk a bit about that since I'm a chemical engineer. And you can also do catalysis to try to reduce the NOx emissions, to reduce the health harm. So first let's talk about the low carbon fuels. The way it's been doing right now is that almost all the jet fuel is fossil fuel from petroleum. But the airlines are starting to incorporate what's called sustainable aviation fuel, which is fuel that's made from biomass. It works fine, and it's a business, and I forget, a certain percentage of the jet fuel is sustainable aviation fuel. And fundamentally, that's coming from biomass and from food waste right now, actually, too. However, this approach, which we're doing it now, has some limitations. So one is if you account for the life cycle emissions, the sustainable aviation fuels are not really zero carbon fuels. They actually have pretty significant carbon intensity, and these are different types of sustainable aviation fuels, and the bars show what the actual emissions are. And so, for example, if you used ethanol from corn as your jet fuel, you could use that to make your jet fuel, it would turn out that the total emissions life cycle would be about the same as using petroleum jet fuel. So you wouldn't actually gain anything by doing that. But some of the biomass routes actually do significantly reduce the CO2 emissions, but none of them go to zero. Also, the biomass sourced SAFs, sustainable aviation fuels, are more expensive than the petroleum fuels. And so this is going to be true for almost all solutions to climate problems, is it's going to cost more. It's not unaffordable, but you have an economic policy regulatory problem of how you get people to go for a more expensive option instead of sticking with the already developed option, which is cheaper. So there's some kind of, they call it willingness to pay, but it's sort of like how you're willing of the government to force people to do it is a key issue. And then last issue is the availability of the biomass. And that's as likely to not be enough biomass or maybe marginally enough biomass in the whole world to supply the sustainable aviation fuels. But as was just mentioned by Christoph, other people want to use that biomass too. Like, for example, the Europeans want to use it to heat their buildings. Some truckers like to put it in biodiesel in their trucks. The people who are driving ships would like to use it. People who are making chemicals and plastic, they want to use it too. So there's going to be a coming war or fight over who gets to use the biomass. But the aviation field is confident that they're going to get it all. So that's the current strategy of the aviation fuel, is just that this is plan A, and it's also plan B, and mostly plan C too, is to get the biomass. Now this raises an issue, is can you do something else? And actually what you can do is you can use hydrogen that you make some clean way and use it to extend the biomass. So you still need to make hydrocarbon fuels to run an airplane because they're the only fuels that have high enough energy density to drive long distance aircraft. But you can make hydrocarbon fuels by taking biomass and adding a lot of hydrogen, and that actually conserves the carbon atoms in the biomass, and so you get more jet fuel for the same amount of biomass. So that's one idea. Another idea is you can just try to react the hydrogen with CO2, for example, taken from the atmosphere, and you definitely can do it. It's expensive. You need to capture all that CO2 first from the atmosphere. Not so easy because it's only 400 part per million in the atmosphere. And then secondarily, you need to make a lot of hydrogen because you need 3 moles of hydrogen of H2 per 1 mole of CO2 because you need 2 of the hydrogens to remove the oxygen atoms as water. And so you need quite a lot of hydrogen, which makes the cost much higher. You need much more hydrogen. And the hydrogen is the biggest part of the cost. to make that much hydrogen, if you're going to make it from green hydrogen, you need a tremendous amount of electricity. So you can see that if you go in that route, you're going to drive the electricity production up and up and up, and you won't be able to just use the cheap versions of renewable electricity, but you're going to need more electricity, and so you have to use more and more expensive types of renewable electricity, like, for example, solar energy in Massachusetts, the kind of expensive kind of renewable energy. And again, none of these options are actually zero carbon either. They still have residual emissions, but though of course much lower than burning petroleum. And they're expensive, even more expensive than the fuels from biomass. But maybe the price will go down. So this makes people think, well, maybe we should even just forget the hydrocarbons and switch to hydrogen. And you could do that. You can use liquid hydrogen, and it has a high enough energy density that it can work. And from a purely energy efficiency point of view, it's actually more efficient to just use the hydrogen directly instead of trying to react it with the CO2, for example. However, it introduces many problems. The volumetric energy density of the energy as liquid hydrogen is much, much lower than it is for jet fuel. So you need to use much more of the aircraft just to carry your fuel. Also, carrying liquid hydrogen is a cryogenic liquid, not trivial to carry it around in every airplane, and supply it at the scale of a whole airport is a lot of liquid hydrogen. And so probably you could do it, but it definitely does not look like a trivial thing at all to do this. And then finally, we'll talk about the NOx reduction. And right now, airplanes have no catalytic converter. So your car has a catalytic converter. It gets rid of most of the NOx. Therefore, with the modern car, if you take care of it, you're actually not making that much smog. However, the airplanes don't. They just burn it. So they just burn the fuel and it goes. You could change the airplanes to install the catalytic converters, but then you can't really run a jet the way we operate them now, because the way the jet works is the exhaust is zooming out, and you can't slow it down by running it through a catalyst, because you need the momentum of the jet to drive the airplane. So instead, you have to switch to electric motors driving fans to push the airplane along. Again, it's possible to do it, but again, not trivial. But if you do that, then you can run a central power plant on the back of the plane that actually runs and burns fuel and runs through a catalytic converter to get rid of the NOx. It may well be worth it, though. You reduce the societal harm a lot by reducing all those NOx emissions. So the question overall is, does this whole idea pay off? And again, you should go back to the beginning. I said that the cost we're paying for the jet fuel is really wildly less than the actual cost to society. It's only about half of the jet fuel cost. It's only half of what, because there's so much harm. So if you count those harms as harms to society, all these options actually could really drastically reduce the harm, even though they increase the cost of the fuel, because they could really reduce the CO2 harm and reduce the NOx harm. So any of those options could work that way, despite all their troubles. And the key question is then a societal question, is we have a technically possible path towards zero carbon, or not zero, but very low emission, low carbon, low CO2 effect jet fuel. It's going to cost a lot more for the passengers on the plane or for the people who are buying the jet fuel, but the societal benefit that our medical bills will be lower, people will be healthier, we don't have sea level rise as much. And so the key is like how to balance, and who is like, the society is taking the benefit, but the people flying airplanes are taking the cost. For rich Americans like us, maybe this seems fine, and particularly if we get some nice bucks from the government to help it out, it seems fine. But actually, to make the problem solved, we need it to work everywhere. We need people in India and South America and Africa and East Asia all to be flying airplanes that don't pollute and don't contribute to the greenhouse effect. But we're asking all those passengers to pay a lot higher ticket price. And who's going to force that to happen? And I think this is a critical question. So I think that the posing in the beginning that this was a US-centric thing, I think is a very foolish idea. That we have our own responsibility in this country to make our own net zero target, but the world problem is not solved with things like aviation until it works everywhere in the world. And so that's a key challenge. Thanks.
Okay. All right. Thank you all for coming. So from buildings to aviation, we take you to the power grid. So the issues, many of the issues that you heard the previous speakers talk about are going to be the same. We're going to be looking at it from a different lens, from that of the electricity grid. So the electricity grid is an engineering marvel. So if you just look at what you see in the United States, okay. All right. It's about 300,000 miles of transmission lines, 470,000 megawatt utility scale generation, 20,000 gigawatts of commercial generators, and all of these interconnections are really happening because of very well laid out purview of oversight from what is known as independent system operators. And this is a very, very large scale system, so like something of the order of 10,000 nodes just in the Western and in the ERCOT interconnection. So this huge large scale system has been designed to a T, and there are various components that basically go into getting the electron generated and bringing electricity all the way to you and me. So what is really changing this conversation of this whole path of how the electron gets to us is what brings us all here today. How do we make this net zero? How do we really have deep decarbonization? So now, the kinds of trends that you've been hearing from the other speakers is the same kind of trend that we see in the electricity grid as well. So for instance, the numbers that you see are the targets for Australia going all the way from the current, like 2006 to 2018-19, which is a few years ago, to 2030. You can see that the green pie of the renewables is continuing to increase. So if you take, for instance, a comparable region in the United States, which is what is known as MISO, the central part of it, which is really what you see on the right-hand side of the chart, there too the mix is very, very similar, that you're really going toward increasing again the green sliver to something larger. And now it's not just Australia or United States. These are the numbers that you see for Japan. And from 2013 to 2030, there is again the shift where again coal and other fossil fuel-based generation is decreasing and renewables are increasing. And what you see on the right side is Canada, the Saskatchewan region, and again the numbers are very similar. So this is also echoed by all of the different initiatives that Robert talked about earlier. For instance, Biden administration is talking about a solar power penetration of 45% by the year 2030. So if you now look at the actual U.S. energy mix and look at the different kinds of assets, you'll see that right now, if you look at 2020 kinds of numbers, you can see that nuclear and coal are significant, but then you can see that the projections are really doubling the amount of renewables. And on the right side, the chart basically breaks down renewables into its various constituents of solar, wind, geothermal, and hydro. So these are the kinds of, so full disclosure, these slides, all of them that I showed you so far, are actually from maybe 5 or 6 years old. So compared to those numbers and those targets, we are now talking about kinds of numbers that are actually 100% renewable. So this is really becoming real. And I just highlighted 3 of the states that have been talking about these numbers. So it's not surprising to you that California is highlighted, Hawaii is highlighted, but it's also interesting that Texas is highlighted. So the point is that this is no longer a projection. These numbers are becoming more and more achievable, more and more of a scientific fact than fiction. So the specific town in Texas actually declared, and this was again some years ago, that they're going 100% renewable. I mean, it's a small town. It doesn't take a lot to really go 100% renewable. But still, the point here is that a municipality is taking this initiative to really move away from fossil fuel-based generation. In this particular case, I believe they were looking at a contract they were signing with a wind energy farm. So Hawaii, for instance, again, there's a big push towards 100% renewables with actually announced the closure of the last coal power plant. And the same thing in California, that there is a significant push towards really carrying out the engineering economic analysis to see how you can really have the LA 100 study, for instance, is something that they're taking seriously, that they want to be able to achieve 100% renewable electricity by even 2035. So in all of these, in addition to what's happening in terms of producing electricity through renewables, the other driver is really this push, and again, you heard that from both from the aviation and the buildings point of view, to electrify everything. And here too, if you look at what's happening with electric vehicles and the type of targets that all countries around the globe are introducing, there too you can see that there is a significant, aggressive target. And it's not just limited to vehicles, and Christoph talked about smart buildings and increased electrification therein. And net energy homes is becoming more and more of a reality. So all of these things are actually introducing a different kind of a driver where loads are basic load patterns are changing and electric loads are actually increasing. So what this also means is that there are several kinds of technical challenges that basically affect us to how the electron actually reaches us in a reliable manner. So these challenges basically come because much of the power plant planning and operations is a top-down approach, where every watt that is consumed today at this moment is essentially a watt that is generated right now. So you need to have that balance of generation and demand, which again, you saw charts that Christoph showed you. And so that's something that needs to happen at every point in time, at every point in space, which means that you need to have an idea of what kind of load is it that you will see at a given time in a given location. And appropriately, you need to commission different plants in order to produce that amount of electricity. So that kind of a top-down approach is going to become extremely difficult when there is all kinds of new patterns of consumption. EVs are getting charged, EVs are getting discharged. You have rooftop solars, which are coupled with storage or not. And when the sun goes down, you're going to use that whole generation, or of course, there are other uncertainties due to cloud cover and so on. So given that all of these uncertainties occur, we really need to address several technical challenges. So it's not just producing electricity through 100% renewables. It's also a matter of getting that electricity delivered to the consumer. So that path basically has this kind of a coordination where you've got your transmission system, you've got your bulk generation, and there are basically markets that oversee as to who generates what. And that aspect, then once that is done, all of that information basically then steps down, and the power steps down to the distribution system, and then it reaches you and I. And the only entities that have to talk to each other in order to make this electricity come to us are these. That's it. These guys come together, and that's basically how electricity was produced and delivered to us in the 20th century. Now, moving forward, in the 21st century, there are a heck of a lot of new stakeholders that are entering the picture. So you have renewables now that become a factor. So you've got the demand response, which is the whole notion of flexible consumption. So you've got storage, which means that you've got these batteries that can charge and discharge and provide you with a way of filling in the valleys. And you've got power electronics that provides the interface between AC and DC. You've got microgrids, which are small components that still give you a way of providing visibility to the operators and making sure that the grid is reliable. You've got EVs, which again are essentially storage on wheels. So with all of these new assets and decision makers that are entering the picture, the question is how you can basically utilize a more sophisticated information layer that coordinates how all of these assets are either consuming or producing or storing energy, and have that information layer basically coexist with the physical layer and deliver the electricity. And it's really not a simple problem. It's also a huge paradigm shift as to how we think about how electricity gets delivered. And there are many, many different challenges. Like, for instance, if ensuring that you have power balance becomes challenging because it's no longer just at the bulk level, it becomes highly distributed. And so if you take, for instance, the kind number of buses, it used to be something of the order of thousands, and now it basically becomes 2 million nodes if you take, for instance, an urban scale decision making. So all of these different nodes that you see in there, every one of them could essentially be a decision maker that basically is consuming or generating. And so having that kind of a coordination is going to be non-trivial. So the kinds of technical challenges are that, first of all, you've got these multiple feeders. Each one of these feeders has devices which could be either a battery, or it could be a smart building, or it could be a PV, or it could be a solar farm, or it could be, for instance, an entire EV charging station network that is capable of charging and discharging several vehicles. And so ensuring that these guys really talk to each other properly and have real-time balance, that's one of the challenges. To have, and these kinds of issues actually trickle down all the way to the house. For instance, all of our houses have three-phase electricity, and if you have imbalances there, that produces voltage and frequency fluctuations. A lot of these synchronous generators that used to provide electricity not only are just doing that and it can be easily adjustable, but also they provide this notion of what's known as a rotating inertia. And what that does is it basically gives you the ability to damp out any kind of fluctuations that can occur. Now, as we lose them and we replace them with several small distributed energy resources, we've lost that inertia, and therefore we need to have other ways of introducing damping. And that needs to happen through what are known as grid forming inverters, through smart power electronics, and all of these advances are actually happening. And I also already mentioned to you about this top-down approach, how consumer demand, as it becomes uncertain, as buildings become smarter, and they could be actually producing net generation because of all of the PVs and EVs that might be connected to the system. So that basically changes the way in which planning and operations occur. And therefore, if operators cannot forecast load, then that's going to be essential in order to quantify risk. So all of those things then become difficult. But certainly emerging technologies in power electronics and control and communication can be leveraged. And so I just want to sort of walk you through two short examples that says as to how some of this coordination can occur. So this is a study that we did in a simulation of a city in Japan, and there's basically a distribution grid with a high amount of renewable energy penetration. And the idea there, again, was that all of the different stakeholders, basically, we assumed that there was a market structure where they could basically exchange energy. And this market structure basically then provided a way of transacting energy. And by doing that, we could basically impose a certain kind of locational marginal price across all of these different units. And that gave us a way of basically making sure that you have a way in which you can coordinate this energy transfer and make the grid indeed move towards 100% renewables. Sorry. So the other example is one with a smaller number of nodes. And here, too, we looked at a scenario where we introduced a high level of PV penetration. And again, Christoph showed you the chart about PV generation. And so this is now over a day. And what happens typically is that now what you're saying is the power over the net power load over a 24-hour period. And what typically happens is that, during the middle of the day, you have PV, and therefore that allows the net load to come down. But as the sun goes down, the demand rises sharply, and this is what's known as a duck curve. And so you really need to make sure, as the duck curve ramps up, that you have all of the units appropriately lined up. And when you have this distributed coordination that occurs properly, you can significantly reduce the amount of this ramp rate. So these are the kinds of innovations that need to continue to happen. And so while it's true that you really do have these multiple stakeholders with varying kinds of constraints and needs, there are ways in which we can actually have them all come together and really form this power grid for the 21st century. And this is not just a technology problem. It really is something that requires technologists, economists, policymakers to all come together, because it's not just a simulation experiment. We actually want to deploy it. And this is an infrastructure system that provides service, not just affordable, not just reliable, not just resilient or affordable, but also equitable. And that's something that we don't often pay as much attention to as we should. Thank you.
All right, so decarbonizing industry, and the reason we care about this problem is because the synthesis of industrial chemicals and materials constitute about 33% of global CO2 emissions at present. And so our goal is to decarbonize this difficult sector. And I'm going to share with you perspectives from a major project we're pursuing at MIT. It's one of the Climate Grand Challenge projects that is taking place at MIT, and the goal, as the title implies, is decarbonizing industry, in particular by electrification. And if you look at industrial products, there is, of course, a wide range of them. But if you look at the CO2 emissions from each of these, you can see that 4 of these industrial chemicals and materials constitute about half of the industrial CO2 emissions. So that translates to about 15% of global CO2 emissions coming from these 4 products. And these industrial pillars include ammonia, cement, ethylene, and steel. And in our center, we are focusing on these 4 industrial products by leveraging fundamental research and technology development, and all the way to enabling scale-up. And the approaches that we develop for decarbonizing these products, we believe, can be translatable to other industrial chemicals and materials over time. And I hear that my sons came into the room. Okay, hi to them. All right, so the reason for the major CO2 emissions from these products is the following. The synthesis approaches to making them have been invented more than 100 years ago, and they are primarily thermochemical processes which require large amounts of thermal energy input, which we provide by burning fossil fuels. And as you will see, our approach that will cross-cut the rediscovery of how we synthesize these materials is use of electricity, use of clean electricity where we can find it, and not only the use of electricity to convert that to thermal energy and provide to the existing synthesis processes, but rather use electricity to break and remake chemical bonds, which we refer to as electrochemistry. So if you look at cement first, and the CO2 problem of cement, 1 ton of produced cement emits 1 ton of CO2. And this is about 4 billion tons of CO2 emissions annually at present, amounting to about 8% of CO2 emissions worldwide. And cement is essentially calcium silicate hydrate, so you need to be able to supply lime, and currently it comes from conversion of limestone to lime, and that constitute about half of CO2 emissions from cement already, and the other half comes from the heat that you provide into the kiln. And Yetming Chang's group has invented a room temperature electrochemical approach that enables that limestone to lime conversion, again at room temperature, using electricity, that slashes 50% of CO2 emissions from cement right there. And we are pursuing advances to this technology and ultimately to scale up and implement it in industry. So second is steel. And the way we are currently making steel is by using a reducing agent to get oxygen out of iron oxide as you mine the iron ore. And we're doing that by providing carbon sources such as coal or methane. And thus your CO2 emissions coming to about 2 tons of CO2 emitted per ton of steel that you produce. Alternatively, we can use electrons, electrochemical processes directly to reduce iron ore, to reduce iron oxide to iron metal. And Antoine Eleanor and his team is pursuing this approach both at room temperature as well as elevated temperature electrochemistry to cleanly go from iron ore to iron using electricity. The third, and that is in fact among the chemicals, the highest energy consuming and largest CO2 emitting chemical, that is ammonia, that feeds the world as a fertilizer and also is considered as high energy density fuel, a high energy density hydrogen carrier. And currently we are making it again through a thermochemical process, Haber-Bosch process, where we are providing thermal energy input by burning fossil fuels, and we're also having to provide hydrogen as a reactant, and currently we're producing hydrogen with CO2 emitting processes. So that gets you to about 1.5 tons of CO2 emitted per ton of ammonia that you produce. At MIT, we are again pursuing electrochemical approaches that take nitrogen and water to give you ammonia, either through liquid electrochemical routes or elevated temperature ceramic membrane-based electrochemical routes. And while I'm putting these schematically here, of course, there are research and development challenges that our team is actively pursuing. So the fourth is ethylene. It's second only to ammonia among the industrial chemicals in terms of its CO2 emissions and volume. And again, currently we're producing this thermochemically by steam cracking of ethane or naphtha, giving you nearly 3 tons of CO2 emitted per ethylene ton that you produce. It's a highly endothermic process, a lot of thermal energy input that you have to provide. And alternatives include, again, electrochemical processes, such as electrochemical oxidative coupling of methane. And a key leverage that we can have by using electrochemistry here, as I will show you with a little bit more technical terms, is to improve the performance of this process, in particular, simultaneously improving the conversion rate as well as selectivity to the product that we want to achieve, which is the C2 products, ethane, ethylene here, rather than deeply oxidizing methane. And the OCM process itself has its advantages intrinsically, such as this process being exothermic rather than endothermic, that can allow you to lower the operating temperature and the energy input that you have to provide. But it's not so far competitive, right? And the key challenge in getting OCM to work effectively for ethylene has been, as we try to go to conditions that increase the conversion rate of methane, we're trying to go to higher temperatures to improve the kinetics of these catalytic reactions, we lose selectivity to the product that we are trying to achieve, the C2 products, ethane and ethylene. So can we leverage electrochemistry to beat the selectivity conversion competition? So again, among these, only with ethylene, I'll give you a glimpse of the technical work so that you have a feel for what we are doing also with the other three products that I have described that we are electrochemically resynthesizing. Okay, so OCM electrochemistry, can we do that, and can we really get simultaneous increase of conversion rate and selectivity? And for this, we're adopting solid oxide fuel cell-like electrochemical platforms, so all ceramic, rather cheap materials, and we can directly adopt the materials, for example, for oxygen reduction or oxygen anion transport from the state-of-the-art cathode or electrolyte materials that we are already working with from the solid oxide fuel cell field. The gap is on the methane side, which we refer to as the anode side here, where we need a dual functional material which should be both amenable to electrochemistry, so conducting ions and electrons, but also catalytically active to methane activation and conversion to C2, and that's where the gap is. So our work is pushing advances on that methane side to get these systems work efficiently. And when we do get these to work efficiently, in fact, you can co-produce, say, electricity together with ethylene as a useful byproduct. If you are using air as your oxygen source, or if you are using water vapor as your oxygen source, you can co-produce hydrogen as a useful byproduct together with ethylene. And the key advantage of electrochemistry is that I can control my conversion rate by controlling my current density in the cell and choose a temperature which is lower than conventional OCM that can give you higher selectivity to C2. And can we really achieve this, right? So if we look at one preliminary but exciting result from this work, we can see that as we increase the current density in this solid oxide electrochemical OCM, we increase not only the conversion rate of methane to whatever products we are producing, but also increase in the selectivity to the C2, to ethane and ethylene. And this is, we have a hypothesized mechanism that gives rise to this very interesting behavior. And as you can see, the increase in selectivity to C2 onsets at the same current densities where we are onsetting oxygen evolution reaction, which could be considered as a side reaction, but the intermediates that we form in this oxygen evolution reaction, electrophilic oxygen species, are also important for catalysis, activation of methane, and we think the two are coupled, and in fact the electrochemical oxygen evolution is in this case assisting the oxidative coupling of methane, and thereby giving us a leverage to simultaneously increase selectivity and conversion rate together. And we're continuing our research to actually improve this material and improve also the energy efficiency of the OCM process. So I cannot but talk about mechanisms in my talks, so I had to share with you a bit of it at least. But stepping back at a higher level, we also have to consider an integrative approach where we are not only working on advancing the materials, devices, technologies that go into the synthesis, decarbonized synthesis of these products, but also look for integration among them. In particular, what could be considered as a waste stream from one process could be a feedstock to another. For example, CO2 that is generated from the limestone to lime conversion reaction could be a feedstock for electrochemical ethylene synthesis. Or hydrogen that is a byproduct from electrochemical ethylene could be used for clean steel or iron production. So we really have to pay attention to what are the best techno-economic and systems analysis ways of integrating these different processes. So I'll stop here and transfer to Dennis. So I was told to, so somebody, I think you are no longer after my slides. Let's see.
Are we all on the same slide then?
because I told them to cut here, so I'm trying to look for yours now. I cannot. The cursor is lost.
Where's the cursor?
Yeah, the cursor is lost. We need the technical support again.
It's all one deck, right?
So it's all one deck, but I had a bunch of backups. So, and I told them to cut here if they wanted to put in one deck.
The cursor's gone. So you can't
The cursor is gone.
Yeah, the cursor sort of is off screen.
Oh yeah, it came. Cursor came back, but it's not active.
Oh, there you go.
There we go. Okay, I think we found
Okay, there we
it.
go. Okay.
There we go. Okay. The cursor came back. Good. Okay.
So thanks. Just to reset a little bit here. So why are we interested in this problem? So we can read an equation. So on the one side, what we care about is how we use energy to do the things that we want. Oh, what happened? It's the wrong one. Oh, I see. Okay. How we use energy to do the things that we want to do. What do we mean? What do we want to do? Move people around, heat our homes, make food, all these things. This is the economic product. This is why we care about this problem. What does this come from? It comes from a product of two things. It comes from the product of generating energy and the efficiency at which we use that energy to do the things that we want to do. And the things that you heard of what we heard of the other speakers today are the amazing things that we're doing about trying to make it more efficient. Right? But at its root stock is what you use to generate energy. And if you don't move that, you can't actually solve the problem because efficiency can only ever get to 100%. And this is why this problem is so hard, because right now the environmental impact, in fact, of what happens in energy mostly comes from when we generate energy. Mostly. And right now, we have moved the needle not a single bit, actually, in the world about how we generate energy. We use exactly the same percentage of carbon-based products to generate energy as we did 10 years ago and 20 years ago and 30 years ago. So why does this matter? Because I'm going to talk about the first part of that equation, generating energy. And as a scientist, or as you just look at the numerics of this, what this says is we need to make really big throws at making massive amounts of carbon-free energy. If we don't do it, all the efficiencies are important, but we're not going to get there. Et voila, fusion. This is one of the big throws that you take at this, because it's the process that powers stars in our universe already. And what does it do? Well, it basically converts hydrogen into helium by a nuclear process and releases staggering amounts of energy, about 20 million times what you could ever get out of a chemical process. So we use specific forms of hydrogen on Earth to do this. The tricky bit of this is that you have to recreate a lot of the conditions that happen in stars, because that's the natural place that fusion occurs in the universe. But what you have in this is we've known the science of this for a very long time, is essentially it's an inexhaustible energy source. The fuel is freely available, and it is carbon-free because you basically are converting hydrogen into helium at the nuclear level. It hasn't really been, do we understand the science or the implications of this? This could literally power our entire civilization. The problem was, could we actually come up with engineering solutions and systems that would be able to deliver this at an economically attractive target? So what has happened is that the fusion, I think because of a couple of things. One, there's been an evolution in technologies, which I'll talk about soon, but it's also the drive. Like the drive in this is like, this wasn't a problem that we thought we had to solve 30 years ago, and now we know it is a problem that we have to solve. And this has led to a series of innovations, not just in technology, but I think in the systems, in fact, that we're using, and I'll conclude with that. And you've seen this news. You've seen this of our own news at MIT, at something called the National Ignition Facility. It's been really, really exciting. But I'm going to primarily focus on what we've done at MIT, because that has a particular connotation to, or a connection to, commercialization. And this is one type of innovation. So to make fusion happen on Earth, you basically have to replace the gravitational force that makes fusion work in stars. So you use the electromagnetic force. So what we did about a year and a half ago is we demonstrated a new kind of technology that makes that magnetic force much, much more effectively. And in fact, it was so much more, and it made a magnetic field that's about 1 million times the Earth's magnetic field. And it did it by, when we were running it, it consumed essentially almost zero electricity when it was doing it because it was in the superconducting state. What this meant from an economics point of view is that overnight we had an innovation that allowed a factor of 20 to 40 improvement in the cost per watt that would come from fusion based on this particular approach. And what this also allowed was that we could actually try this thing that's on the right, that is namely, it's called Spark. And what this allowed was a program and actually economic resources to try to make this big throw, because what it allowed us to do was greatly reduce the size of fusion devices. In fact, it reduced it by about a factor of 30 to 40 compared to previous technologies. That's the kind of breakthrough technical innovation that you're looking for when you're trying to both go faster but make it economically viable faster as well too. This wasn't just technical innovations. This was also I would call institutional or organizational innovation as well too. Because the idea of this was a company that was spun out from MIT, which we do all the time, but was actually tightly coupled to the research endeavor at MIT because of the difficulty of the integrated technology to do this. So it was a joint team between the company we spun out at MIT that developed this technology about a year and a half ago, and then a few months later, the company announced that it had raised almost $2 billion to, in fact, go after this unique energy solution. But part of this plan all along was that it was a plan. It was, we're going to step through these innovations in a particular order because we believe this is not only what the science and technology asks for, this is what the market will ask for. So right now we're in the middle part. We're building this thing in the middle called Spark, which will demonstrate net energy from fusion in the middle of the decade. But the end goal is actually to do what I said at the beginning of this, make massive amounts of carbon-free energy, and that's done with a thing which is on the right, which is essentially a commercial scale pilot, which would do that. So what does it look like? So this is happening, now. So Spark, there you can see it. You can see the people standing beside it. This makes about 150 million watts of fusion power. It has net energy gain at a commercial scale for the first time. And where is it being? So it was designed at MIT, by MIT and the company we spun out, Commonwealth Fusion Systems. And I always like this picture the best because you know it's real when you're pouring concrete. So this is the site, which is 45 minutes outside of Boston, that's run by Commonwealth Fusion Systems. The large building over on the right contains the fusion device, and the large building over on the right contains the factory, which is now making the magnets that were developed at MIT at a commercial scale. So within less than a year, we actually had a commercial facility that translated the technology that was being done at MIT. That's also what because unfortunately it's not just about economics, it's actually about meeting the demand as fast as you can as well too. But it's not just about Commonwealth Fusion Systems. This has spawned, although we weren't the first to it, I think we can take some credit for helping spawn what is essentially now a new industry in the United States, which is, it turns out the physics of fusion allows you to get after in a lot of different ways. And what's amazing about this is that I would call it the entrepreneurial innovation spirit of the United States and the world is actually opening up. That now we have over 25 companies pursuing different kinds of approaches in fusion around them. One of our own spin-outs, which is there. But it's interesting is that this is amazing. I never thought I would ever see a plot that looked like that actually in my in my professional life. But it's also interesting about what's missing in it. And what's missing in it is that these are science-based companies largely that are looking for a clever way to basically reach the conditions at which net fusion energy will be able to get you there. But there's almost zero companies that tell you actually how you deliver the energy. And almost the topics of what we heard in the previous speakers. How do you take a raw energy source and deliver a product of energy to a consumer market that actually will respond to it? So the answer is about, this is one of the things now, since we spun out Commonwealth, this is what we're starting to turn our focus towards at MIT at the Plasma Science and Fusion Center. And it's based around this essential platform, which is this uses that magnet technology to confine that very hot plasma and to extract the energy which comes from it. And just to put a little bit of context on it, it's pretty amazing technology. You can see the people standing beside it. This basically powers Boston. And it uses, has 0 carbon emissions, and the fuel that it would use in a single year I can carry in my arms. That's kind of how amazing fusion is. But we need a next wave of innovations, because now we have in front of us the opportunity that actually it looks like we could meet economic requirements and economic competitiveness to meet that demand, make massive amounts of carbon-free energy. But it's going to take a series of coupled further innovations. This is always what is fascinating about it. Once you're on the innovation cycle, it never stops. Like, you have to keep innovating over and over again. And what does this look like? Well, I actually pointed an arrow at a few of these, which I won't go through the details of these. But basically, you look at the upper right corner. What you need to do is, in fact, extract heat and basically make this special fusion catalyst called tritium in a very effective way. You actually notice some similar words that I was using to what Bilge was talking about. And actually the reason I put up this slide is it shows you why then you need to expand the ecosystem at a place like MIT about the kinds of disciplines and the kinds of expertise you're starting to bring to this. It's not about just magnets. It's not just about plasmas. Sorry, Anne. It's about the entirety of the system as well too. We also think about the materials that we have. So one of the interesting challenges of this is that not only don't we quite know about what materials we should use, we don't even have a methodology to test those materials. So in fact, we're now looking at figuring out rapid new innovations in how you prototype materials in a time scale that actually makes sense towards all those things. I'll go to the bottom right one, which is an interesting. There was also, you saw comments about decarbonizing or getting to net zero in airport and airline transportation. Maritime shipping, an extraordinarily large fraction of what we do. But how would you do that? So this was an interesting innovation that came in my class, where we considered aspects of using fusion to produce large amounts of hydrogen to make carbon-free ammonia fuel, and what that implications would be for that and around and that. And I have to conclude with the final one, because it's MIT. Like, what's the other innovation that we need? It's actually not in the technology per se. It's about how we educate ourselves as leading scientists, but also obviously the next generation of people who are coming along. We have to give them the tools, resource-wise and otherwise, about how we actually, because they're so motivated to tackle this problem, we have to give them that part. And so we need to be thinking as educators all the time about how we innovate in our structure to empower them so that we can get to that answer. Thank you.
Well, thank you all so much for taking us really into each one of these areas. And so I want to leave some time for the questions from the audience. And so perhaps for the discussion amongst the panelists, since you've all alluded to this in some sense, maybe you could each of you take just a minute or two to say a few words about opportunities that you see for synergies and collaborations between your areas. So I don't know if we want to come down to Christoph or Bill first. We'll start down there.
Sounds good. I think a lot of the presentation also alluded to the connection points that we see. When I think from the building sector, it's definitely the looking at net zero steel and concrete, because obviously the buildings are a major user of this. And I think it becomes really interesting when you look at both how do you use the material more efficiently within the building, as well as obviously have access to affordable concrete everywhere, right? And I mean, I really loved the presentation, Anu, which showed how buildings are just an integral part of the smart grid. And right now, I think we are failing really of realizing that on a large scale. I think we have Teslas in the driveway, but right now we delay the charging, but we never discharge them because we are so afraid that we might run into liability issues. We know the enormous potential if you would just change out, doing a heat wave, the thermostat settings from everybody for half an hour just by 2 or 3 degrees Fahrenheit for half an hour before you move it back. You could tunnel through the peaks. There are so many opportunities, and we've been talking about them for 8 years, and they're still not there, and hopefully this is coming now.
Oh, thanks. Bill?
Yeah, so I would just comment that there's big connections. I mean, in fact, Bilge and I are already working together, and I think that all in the chemical materials and fuel space, you're trying to make a stuff with matter, and you need to make all the atoms balance and end up where you want them to be. And whatever you do to change one industrial process, it's a big scale process, is going to have all kinds of knock-on effects on all the other processes. And so this is like a very coupled and complicated chemical engineering, material science kind of problem of how to do that. And then in the background of all the work that we do, we're assuming that someone is giving us this nice electricity. And so I think that Dennis's and Anu's talks are really very important, that the whole presumption of the society is that there's going to be green electricity, lots of low carbon electricity. But in fact, even in California right now, you're still only about half the CO2 emissions of the grid in the rest of the country. And to think of how to go further, it gets more and more challenging as you try to squeeze out the emissions. And so I think, actually, for me, I always think that people say this net zero thing. I think it's like a lie. It's like really the path we're on, if we're really good, we'll get to 90% reduction, maybe 95% reduction. But there's many, many little things that we don't really have a good plan yet for. And I think that's okay. You know, I feel like the people in 2023, we don't have to solve all the world's problems all the way. There's some more engineers and scientists and clever people going to come along later, and we can leave some problems for them. If we can take care of 95% of it, you know, I feel like we've made somewhere. I don't think we have to claim that we're going to have the net zero for the whole world. It's just not. I think it's a lie to the students to say that, because we really don't have a plan for that. And certainly the politicians, they can say it because they'll be out of office before they get to the date, so it's okay. They can say whatever they want.
I think that I would cite two examples in terms of synergies. I mean, just this panel, none of us really compared notes before we came here. And it's really interesting to see that, you know, some percentage of the slides could have been part of any of our presentations. And so right there, I think, is a great example. And to me, it's really fascinating to see that, you know, if we had had this panel about 5 years ago even, probably the kinds of numbers that we would have had up on the charts would be quite different. Not maybe entirely different, but quite different. The fact that, you know, at least just in terms of the electricity grid, the numbers are talking about 20%, 30%, 40%, to really actually say 100% renewables is possible, that is, I think, 5 years is a very short time in the scale of things. And so that is, again, I think, tremendously heartening. And those kinds of movements in terms of targets are happening across all of the different sectors, which is also fantastic. I'd also say one other thing, and Robert mentioned about the Future Energy Systems Center. That, too, I think, is really a forum for providing the synergy. There's been a lot of presentations that from different, domains, and it's at least I've been learning a lot, listening to them, and, you know, identifying the kinds of opportunities that Christoph, you mentioned, and you know, electrification of industrial processes. So I think we're in a very good place.
Okay, synergies.
Yeah. So some of this is already mentioned, right? Concrete and steel, you need them for buildings, and you need to get them decarbonized. They're also essential for building power plants, such as Dennis showed in the fusion plant that they're actually building. So materials connecting to buildings and clean energy plants is obviously there. And Bill also mentioned the inherent connection between decarbonizing industrial chemicals and fuels, where there are cross-cutting catalytic, electrochemical materials and processes that benefit both and can be co-developed. And one key connection that I want to mention with power grid is, so I talked about electrification of these industrial products, right? Right now they are produced via thermochemical, large-scale plants, but if you go the route of electrification, then they can also become more modular and distributed. And that has to be worked out, like where to site them and where to leverage the green electricity has to be coordinated with how the power grid will evolve, depending on where these chemical, decarbonized chemical synthesis plants will be sited, right? And another connection that I want to point to fusion is through electrochemistry. So as Dennis shared with you, tritium is key in the plant, and through fuels and chemicals, we're saying that we can deal with hydrogen, electrochemistry. We know how to move hydrogen electrochemically. We know how to convert hydrogen electrochemically. So some of these can also be translated to controlling and managing tritium in fusion plants. And we're also discussing about this with Dennis. And I'm also happy to see that you're connecting to fuels and hydrogen and ammonia as products beyond electricity. And again, those are very exciting connections.
Yeah. So Dennis, do you want to say a few words about synergies, or do you want me to ask something more provocative?
Oh, I'm gonna say something more provocative. Okay, that's why you asked me to these panels. So I propose a different kind of synergy that is required, and I think you have to ask the question, like, why are we failing so badly at this? And it's not just that we don't have massive amounts of carbon-free energy, because there are some other interesting choices about what we have. So what I would say, and the things that you talked about are correct, which are synergies around, we share disciplines because energy tends to be a multidisciplinary thing that you've got to attack. But I'll point out the synergy that we need in some sense about how we think about the products that the energy will make. And one of the reasons I think that we're failing is because we're trying to do two really hard things at the same time. One of them is to produce, it actually goes back to my two parts of my equation. One of them is come up with new ways of generating energy at its rootstock, right? So that's going to be hard technologies like fusion, enhanced geothermal. But the other part of the hard problem is you have to deliver and use the energy in the economy. Right? And so I know to solve decarbonization, one of those things has to be true. Like, it has to be at the generating part. The physics of that is true, right? So what I'm skeptical of is that we make massive changes also in the infrastructures that we would call about how we expect as a society that we deliver and use that energy to make the things that we want, which is economic, interesting economic things. So where I think that the synergy is stop thinking about the new energy sources as a thing which is sort of separated from the things which are delivery. In fact, where I would say the synergies are is we need to go out and figure out how all the new energy, because we have to make new energy sources, but how do we adapt those new energy sources to be as compatible as possible with everything that we have already in terms of energy delivery? So could we actually do this? Like, could we not completely mess up the aviation world? Or could we actually keep working in constructive way? All the things that we were talking about today. But this means it's a greater synergy about what our end goal is. And I think if we don't do that, we're not going to get there. Because it's just going to be too much to try to do those two things at the same time.
That's great. I mean, other comments in this theme of, innovations that we really need that weren't necessarily covered in this panel, right? So we heard about the end product, the end use thoughtfulness. I mean,
sorry, say that again.
Other innovations that weren't covered in this panel.
Oh.
And anything you see that might be out there, something MIT excels in, but something the world needs, something the country needs. But we didn't touch it here.
Okay. You want to, okay. Grid and transportation are joined at the hip. So we certainly, talked about aviation, but there's a lot that I think we can talk about in terms of, say, for instance, looking at the synergy between EVs, fleets of EVs, and the power grid. So that shared mobility on demand and connecting that with renewable energy. Those are, I think, there's a lot of interconnection there that we could really talk a lot about. Hydrogen is another thing that, yes, we touched upon it in different ways, but I think it's really becoming in its own right, becoming more and more important and, again, pervasive in terms of a new energy source. So that, I think, is, again, something where we have fantastic innovations going on here at MIT.
Christoph and then Dennis.
Yeah, I think there's clearly what we haven't talked at all about is lifestyle choices and urban planning. I mean, that person that buys the electric car, we assume we have to live exactly the way we do right now. And if we look at it, we are not a really happy society, statistically speaking. So maybe that's a bad idea. Why does everybody need to have a car? And there are 4 people living in a house, and then they're empty nesters, and nobody uses the house. I think more a reflective way of how we reimagine and design our cities to provide access to everybody, like modes of living overall. At MIT, we had the future of work. People, why do we accept that we have to build 50% of this country again in 30 years? That's like a really stupid idea, given how many buildings are empty in Manhattan everywhere. So I think we should really more look at these choices, right? Most people don't want to come to work more than 3 days a week. I think we need a lot less buildings than we think, but we have to think about it now, right?
I think we need innovations in what we call informational policy, information-informed policy. It was a great example, which actually was commented to. So how many people know that the actual cost of the fuel that they're using in the airplane that they're traveling on is actually twice like what the airplanes are? So this is amazing that we have lack of information about what it means about how we use energy, and we also we have total lack of cohesion in our ideas about how we build financial policies around the way that we use energy. Like, how are we ever going to get out of this if we don't have clarity on this? But we seem to refuse to accept the political, it's going to be an interesting political challenge, but it's also, I would argue it's a scientific one, because it comes into how you get transparency about something which is complex as energy use. And until we get there, it's like, how are we going to adapt our behaviors to, in fact, know that if we're information free, which we largely are at this point.
So, anything else, Bilge or Bill?
Yeah. So you ask what MIT excels in. So whatever the target, I think we all recognize MIT excels in blending basic science and engineering innovation. So whatever the target is, as hard as they are, as long as we stick to that aspect of us that we excel in, I'm maybe more optimistic than Dennis in getting there. We are not failing.
Maybe I'll end with a negative note then. So I'll be the downer guy. I've been working a lot on trucks, and I'm trying to find a solution that will work for trucking in all countries. And so then you think there's millions and millions of individual owner-operators that have trucks all over the world, and it's their major asset, and it's their livelihood. And I want to persuade them to change to something else, to drive something else that's not going to hurt the environment as much. But if I pose it that way, it's quite a challenging thing, right? Because whatever I propose, I need them to buy a new truck, probably need to get their new fuel. So I need to persuade the truck stop to change. And so who's going to provide the money for this? And then how am I going to, if it costs more, how am I going to prevent people smuggling and going on using the old trucks? So I think there's a lot of social science complexity. So as the engineer, I've just been working on trying to make my solutions cheap. So it's not so hard to imagine you could bridge the gap, and that's important for sure. But I think there's another whole thing which I don't know about, is how you would have a policy that would actually be effective in all the countries of the world, and for millions and millions of individual actors to comply with it. So I think there's a big part of maybe social science part that has to be also developed as much as the engineering.
Or even worse, we're hypocritical. Tell them you can't drive your truck because it's going to contribute to climate change. Well, we've built all of this and become the richest civilization in the history of the world, but none of you else could have it. I think that's the moral part to this as well too, which is, I think, is largely missing from this story.
This is good. We have optimism, we have pessimism, we have the push, we have the pull. Without the tension, I'll be in the middle. I'll be in the middle. Without the tension, we don't get anywhere. So we're on time for audience questions. So the push and pull of the speakers in the audience. So we're going to have someone bring a microphone down. So I see you, sir, here, and then, yes, recognize you next. Thank you.
Hi, thank you. So we can look forward to another panel with just social scientists next time.
Yeah.
But my question is, we had a lot of big wins legislatively last year. They were mentioned at the beginning. And I'm wondering, is there another piece of legislation you're all looking for that needs to build on what we did last year? Or is there another policy that you would like to see implemented at the federal level to further boost all of your efforts?
I think it will be very hard to ask for more money. I think this is a generational opportunity where we got enormous amounts of money being pumped into it, and we better don't mess it up. I think the distribution of these funds is not really well thought out right now. I think in the building sector, we know it's going to perpetuate inequality. There we have these folks, as I described, that are going to have in a couple of years, or even now if they want to, have zero utility bills and costs of driving around, and large swath of society will work with integrated technologies. So I think there's a lot of work we have to do right now in order to make sure that these funds are being allocated in an equitable fashion. And a lot of people, fortunately, are talking about that, but it's not even that clear how to convert that into enforceable legislation. And I think there we need a lot of help.
So we saw another question up there, and then I'll come over here. Yeah.
Much, very interesting session. Question on digital technologies and the data layer and sharing of the information across all the players that either produce energy or consume energy at different prices during the day, being able to optimize, predict, etc. Shouldn't we also consider both about the innovation in that space, more innovation in that space, as well as more legislation in the space of allowing to exchange the information in order to kind of, as a society, to achieve better use of it?
I'm not sure I heard the last part. So you're talking about sharing of information for consuming?
Yeah, so in Europe, and some of the countries in Europe, they're passing a legislation right now where they are allowing, including consumers, to share their information when I turn on, my heat, or when I want to charge my car in my house, so that I can send that information to the grid and they can give me advice on what is the best time of day.
Okay, so you're talking about privacy issues.
So there is an issue of privacy of the information in order to make that information flow freely.
Yeah, you bring up a very good point. I mean, as what's happening definitely in terms of grid modernization, smart grid, is that there is democratization going on. So there is definitely public and private partnerships that will happen more and more. And so from that point of view, the template for delivering electricity is really undergoing a major transformation. So the flip side of that is the privacy issue, for instance, that you mentioned. And so it's not, the answer is not going to be 1 or 0, and I think the answer will be probably a sort of a continuum of solutions. It might be that for normal operation, that you really don't have to give out, there's no disclosure at all, and you're completely protected, and there's technologies that are being developed with different domain expertise that allows you to keep your information private, but still have some sort of obfuscated, aggregated information about consumption made available to operators. So that can happen. But let's imagine that there is a big storm, and then you've got a cyber attacks, and so then when things are, when your back is to the wall, you might need, in order to have a resilient grid, some amount of information that you have to share. So in those cases, privacy probably should take a backseat to resilience. So I think these kinds of different templates for solutions, I think, will necessarily have to emerge.
At the core of decarbonization is a massive uptake in solar and wind. There's an article in the Times this week about how the political blowback about generation of wind and solar in the heartland and the rural areas. The question that comes in, we have a political policy nightmare here such that all those assumptions about solar and wind growth may not be politically even remotely possible. And if fusion doesn't kick in until the 2040s or 2050s, is traditional nukes really the bridge?
Yes. It's actually not just a policy one, it's a physical one. There's a physical limitation, not just because of the deployment and the land use that is in play, but the intermittency, which is in there as well too, which is in fact is another aspect of the technology approaches going on at MIT, because the storage solutions are not at scale, not at economies as right now. So, my vote is you have to use whatever large carbon-free energy source you have right now, which is deployable, which really is the thing that fills in the gaps to renewables. That's nuclear, like right now. So we should at least maintain that capability, I think, around these.
Yeah. Thank you. Aag van der Meij, researcher at LITS here in Stata. You're speaking about fusion, and you're talking about matching this up with consumption. That it fits with the demand pattern. One of the big things that is staring at us for this net zero future, is the carbon capture.
Yes.
And some recent numbers put this at 10,000 to 20,000 terawatt hours to capture 10 gigatons.
Yes.
Could that fit with the Commonwealth systems and with those new modular fusion reactors?
Yes, to a point, and that's actually was my comment as to the synergies have to happen in that as we go down the paths to making technical, because we can't pursue infinite number of technical decisions about fusion. We have to come to some decisions about the form of the energy that we're producing. Fusion's not an electricity source, it's an energy source, but the form of the energy, for example, the temperature, the chemical composition of it, all of these things really matter as to what you can use it for effectively. This isn't just around carbon capture, desalination, production of fuels. All of those things are on the table, and we have relatively poor insight at this point, in fact, into those things. But yes, those, yeah.
So come here to the front, and I see one in the back. So,
thanks. This is a great panel, and it's always fabulous to see how much talent there is in all the different scientific departments at MIT. And I know this is just a slice. We run a nonprofit, for all disclosure, working on fusion and working on my question, which is, since I've heard in a number of places the word silos of information and information flow, even within this ecosystem of MIT, and I know that you have, for instance, a climate discovery or challenging algorithm that you built called, En-ROADS, which when you ask right now about fusion, there's a zero possibility of it. So even within MIT, we have these barriers, right? And that's human. That's what we all do. We silo. We're working in the large arena of humans. So we're not just social science. We're actively talking and working with both young people, which our educator Kayla works on, and people of all different professional capabilities. So how do you, having these solutions that if we network with them all will at least move the needle significantly, how do we get those solutions into the belief systems of the people that need to make the decisions? Because we're not theoretically, we're not an authoritarian entity. You can do something in a university setting, but you can't do it on the American political scene or actually in many political spaces. So how do we do that?
So, Christoph, I don't know you.
Yeah, I think generally cities are a great spot to start working in because, of course, when it comes to building, local transportation, a lot of is being created in cities. And we felt an enormous appetite so far. We were, in our lab and many other labs work with other cities. I heard we work with cities across the world. And right now, since there is this strong political mandate right now to get to net zero, you find basically the sustainability champions in cities everywhere. They have no idea what to do next. Basically, they were told they have to get net zero and they are scared for their job. And so for us to start working with them, developing different technology solutions, I think that's a good size cities are complicated and political beasts, but small cities are way better than big cities. But I think that's a good entity to start off with. And I think I find it interesting that Dennis says, oh, this thing can power Boston. So I think this is kind of these are natural units to think in.
You bring up a very good point. I think all of these are infrastructure systems that we're delivering as service as a society. So most certainly humans have to be very much involved in the conversation. And it's happening there are pushes and pulls that are making it happen, and which is really heartwarming to see. I don't know if you noticed the very last word I used in my talk was, we really need to develop an equitable grid. And so that is very much, a societal issue that has to be addressed. And all of these technologies are ultimately for the society. And so bringing in those kinds of elements, like for instance, energy justice is a topic that is being discussed quite a bit in Department of Energy, has several initiatives that is going on, and of course, National Science Foundation. So there are consumer advocacy groups that really are trying to address how these disadvantaged communities, the low to middle income people are really benefiting all of these, and enjoying the benefits from all of these different technologies. So I think it's just as important for, these advocacy groups to be really here and be part of the conversation in order to move it. And it's happening. And there's a whole branch topic that is emerging, which is called cyber physical human system. And so how do you design these systems in a way so that it's efficient? So those discussions are happening. And I think more of you have to come to this panel here perhaps and start that discussion going with some urgency.
Well, actually, can I just, because I want to give a shout out, to the host of this event. In the end, this is what the Energy Initiative is built for. You need a place where it's really hard, by the way, because everyone's really busy. You're working and you have to do that work because you have to get things done. But we need a gathering place that is where we can exchange the big ideas and the small ideas at the same time. And it's a great thing that we do have the Energy Initiative. I think it really means, though, that we need to be thinking continuously about how we upgrade or update our institutional innovations that allow us to become even more effective at, in fact, finding those solutions. So thanks to everything that Mighty's doing. That's great. Yeah.
Good. So I think we have time for one more question, but there's a lot of hands. So
it's working?
You're
okay.
On.
I'm looking at the title, Energy Innovation for a Net Zero Future. I'm almost tempted to add for whom? Because to make what we discussed happen, there is going to be an exponential mining of the aluminum, the bauxite, the manganese, the copper, the lithium from many parts of the world, people who will not see the benefits of this net zero future, because many of these items we do not have here in the United States. There are supply chain issues that are in the way of this issue, but also the people who live next to these mines in Kazakhstan, in Australia, in Zambia, their lives are going to be affected forever. Yes. In Bolivia, in Chile. So from what the gentleman said up there, I think the next time there should be a social scientist among the scientists to discuss these issues. Because I visited some of those places. When you see some of those mines, you will never want to see another ton of bauxite mined from the ground. Thank you.
Right, but actually this comes to the technologies. In the end, so this is why you use something like fusion, right? Because you get 20 million times more energy per unit of mass of whatever you're putting into the thing, okay? So the environmental impact around mining, around social energy justice is just staggeringly different. It's not zero, but it is staggeringly different than actually many of these other things, including the use of fossil fuels. And there is a price to pay even in so-called renewables as well, too. We have to accumulate this up. Again, this is the role of Energy Initiative. We need neutral arbiters in this. We all have our favorite things that we like, but you need actually to keep score in an appropriate way around those things.
Yeah. This is good. So we're at time here. So I think we do want to just recognize, thank the audience for coming and having this discussion with us. So thank you. I also really want to thank the panelists, all of them, for these fantastic talks. And I think really just close by saying this pillar of innovation that we heard about today and the crosscuts there and the bridges out to the rest of the bigger questions is really a big part of what MIT is trying to do with the climate action plan for the decade. And beyond innovation, it's about what are we doing for our own carbon footprint on campus. It's about education. It's about policy. And one thread which weaves it all together in the climate plan is justice. And I think these are conversations that we will keep having with all of you, with our community, as we solve these problems together. So thank you.